and tectonic geomorphology. And so this is a quick lecture on topographic metrics and bedrock channels. So it's you might do this a little bit earlier than the trenching. So this would be in an earlier kind of regional characterization phase, or looking at larger scale landscape evolution around active faults. And so the things we may want to, that I'll talk about, are quickly about topographic metrics, and then the main thing is fluvial scaling and slope area relationships, and then how one of the metrics called channel steepness is very sensitive to rock uplift rate. So topographic metrics are just measures of topography, anything, slope, relief, various combinations. And so there's the most common that seem to be useful are channel steepness index, hill slope gradients, and local relief. And one question we may ask is, well, what is the relationship between these, and which is the most useful for gauging the influence of tectonics on topography? So one point that, and most of this work, this PowerPoint and these ideas come from my colleague who is at our university, is very famous for developing a lot of these ideas and explaining them in the last 10 years. His name is Kellen Wiffle. And so one point he makes, and one thing we'll experiment with this afternoon, is most of the relief in the landscape, so relief just means the elevation change, is in the channel network. It's not in the hill slopes. And so therefore, the channel network may be the part of the landscape that's most sensitive to large-scale rock uplift differences. And so here's this idea of the fluvial scaling. And so if you look at just many rivers around the world, they tend to have this relationship. So first, let's just look at a longitudinal profile. So this is us just going down the river. If we were in a boat, we would start at the top, and as we go, it's kind of steeper at the top, right? And as you go downstream, the river may get larger because of increasing contributions from tributaries, which means that the contributing area is increasing as you go downstream, but also the slope is decreasing. So it's steeper at the top of the drainage and less steep at the bottom. So this is elevation versus distance, but another way you can represent this is the log of the local slope versus the log of the area, the contributing area above that point. And this ends up having a pretty linear relationship in lots of topographic data, where the slope is a negative power function of the area, and it has these two parameters, the Ks, which is the channel steepness, and the theta, which is the concavity, which I'll explain in just a moment. But let me just quickly draw what I mean by increasing area. So here's the actual data from Eastern North America, and basically computing the area and plotting it versus the slope. And we see that the very top of the drainage is steep and doesn't quite obey the same rule. And that's probably because this is maybe where it's so steep, the rocks are coming down, it's more debris flow. But the regular fluvial, or river part of the system, is right here, and it has this relationship, and there's the concavity. So this is, in geomorphology, they call it Flint's Law, named for famous geomorphologist. And so there's the transition there. We have a colluvial reach, so that's just the very top in the mountains, the top steep channels that are dominated by colluviation, and then we have the regular fluvial system. There's the concavity, and the Ks is our sort of position up and down for that line. So the Ks seems to be a more general index. It doesn't seem to depend on the shape of the drainage or the size of it. And so here's some other work that was done by other scientists following the work of Wiffle, and Kirby was Wiffle's student. And so what they showed was that this, just to make things simple, if I hold my hand this is the concavity. Okay, that's changing concavity. And the steepness is for a given concavity. Is it like this or is it like this? So my hand isn't changing shape. It's just, is it steep or less steep? And so what they showed then is that the steepness, and now this is the main point of my lecture, this Ks seems to vary with uplift rate, which is U. And so for a higher uplift rate, the channel will be steeper, even though it may have the same concavity. So if you lift it more, in order for the channel to remove the material that's being fed to it, it has to be overall steeper. So I'll present that. And this work was done in, I think, a famous paper by Wiffle and his student Eric Kirby. And so what they did is they went to Nepal, and there's this fold here, these hills called the Shivalik Hills, and they're lifting up. And there was really good information about the uplift rate across the Shivalik. And so they studied these rivers here crossing. I think I have a better picture in a moment. But what they did is they built on the work of LIPI and Ozwalk, who were basically studying the structural geology of that site. And the river crosses through these hills, and the hills are basically a manifestation of this folding above this thrust fault. And so what these figures show from LIPI and Ozwalk is they dated the terraces that cross the hills. And the Bakaya and Bagmati transects are two different rivers. This is Bakaya here and Bagmati there. And as you go in these rivers, there are terraces, and it's a little bit hard to see, but they'll be on the sides of the valley. And they dated them, and this is shown in uplift rate, not total uplift. And so they get the form and basically plot distance versus that uplift rate, and you can see it's pretty constant. So each of these different terraces seems to show the same uplift rate across the fold. So this is distance across the fold, and then this is just the back limb on Bakaya. So what Kirby did is he then looked at especially these drainages like 20, 19, 17, 18, 16, 14 that were in a part of the fold that was lifting up. So basically he has a drainage like here that's on a low uplift rate place, and that drainage here that's in a high uplift rate place, and the drainage that's there in a low one. And it's parallel to the fold, so the whole drainage is lifting at the same rate. So these drainages here that are perpendicular to the fold he didn't use because they're going across an uplift rate gradient. And what he showed was that for two of the channels, one that was in a 7 millimeter a year and one that was in a 14, in this slope area space, the one that was in a higher uplift area had a higher steepness. So it was tilted more. And what I mean between those two is that would be the difference between maybe like 18 you see is right in the top of the fold where it's in the full 14 millimeter year uplift, whereas 19 is on the side of the fold where it might only be 7. Okay? So that's what these two are trying to show. And so then when they looked at all of them and they did steepness versus the uplift rate across the fold, they showed that really the Ks, which is this axis here, versus U had a pretty linear relationship. So it seems like, and to me this is what's really revolutionary, is the Ks is just topography, it's just the shape, but it seems to be very sensitive to uplift rate. So it's a really powerful way to use geomorphology to map uplift, assuming all things like constant rock type. And so one place where they applied it was in these mountains here in North America, in California, called the San Gabriel Mountains. And so here's the San Gabriels with just color an elevation, and then these lines are active faults, and the fatter the line, the more active. So here's the San Andreas fault, but here are some thrust faults in the front of this range. So it's the thrust fault bounded range is lifting up. And so what they did, well, let me just jump ahead. So they could color these maps show the steepness index, so the KS. And the main thing to just see is where it's red versus where it's green. And so there's lots of steep channels over here where we think the uplift rates are highest in the San Gabriel Mountains. And then the greens would be places where the uplift rates are low. So then what they also showed was just local relief. So I showed this before, but the relief is just you go across the map and you take a minimum and a maximum, let's say within a 500 meter radius. And we say, okay, well that relief is a kilometer, let's say, and we assign that to that value on our map and we go to the next pixel. And so that's what the white is showing. The background map is the local relief. And so you see these circles, kind of shows the search radius. It was about, looks like it was maybe look at the width of this radius here, probably 2.5 kilometer search radius. And so you just move that around, and within this radius, you say max minus min equals relief. And so in the same places where there had high channel steepness, had high relief. And so this would just be a piece of the mountains that were just really deep canyons, steep rivers, and where the rocks were going up fast. And so this approach, many people have been doing. This is a paper that these guys wrote where they describe how to make these calculations, how to do the channel steepness calculation, how to make plots like this one. And I'll talk a little bit more about that this afternoon. But this would be a morphometric index, channel steepness, and in this case it seems demonstrably related to rock uplift rate, which is not every index will do that, but that's what's a really powerful thing about this approach. Good reference in a special paper. It's like a book from Geological Society of America. The one thing that these guys showed, Kirby and Wiffle, here was that this is all the same rock type. In the fold, it's the sedimentary units on sandstone. And so because the KSN will also vary with lithology. So you could have, if you have constant uplift rate, then you may have a higher steepness on harder rocks and lower steepness on softer rocks. So we have to correct. So usually this only is applied when you're comparing basins on similar rock types. Or at least you have to be aware of the fact that you may be crossing into another rock type, and so this relationship may become more complex. I say different rock types, but it's not just that it's the 100 million year old granite is different than the 5 million year old granite. Maybe all granites are behaving similarly, and all basalts are similar. So it's more the erosional characteristics are what we care about. So if they're difficult to erode versus easy to erode, that's where both are controlling the morphology, both the rocks and the uplift rates. So if the uplift rates are low, then the landscape really is just showing differences in rock resistance. But if the uplift rates are high, then the rock resistance becomes less important. You can kind of see through it. So it's that's the way I think of it, relative rates. You only need extreme differences in precipitation to really change the behavior of the system. But overall, the geomorphic conditions will be different if it's just by climate. So semi-arid conditions, the soils will be different. The way the rivers function will be different because they may not have sustained flow. In very humid environments, the weathering rates are really high, more vegetation, steady runoff. So again, that's why it tends to work really well in kind of regional applications. So you can't take KSNs from, one place in the Himalayas and apply them somewhere else where it's totally different. But internally, here the climate gradients are small and the rock types are constant. So the only thing that's changing is rock upward freight. So then it works really well. But if you go wider and wider, you have to worry about these other things changing.